Hey guys, welcome to the second video on the visualization of the model results. Why do we do this? Again, one picture is often worth 1,000 words. And in this video, I will show you the most compact code which will give you most of the results of the visualization of models. If you didn't see the first part, I highly recommend to see it first, because there I introduced the most important functions and concept. Without further ado, let's get straight into it. The last part finished with the visualization of several linear models on the same plot. So the consensus here that a lot of things are not really linear. We could linearize it, however, with some technique. For example, logarithmizing the salary variable. It would help. The interpretation will be a bit skewed, but we could solve this problem of nonlinearity. Or we also could solve the problem of nonlinearity with the polynomial function to force the model be nonlinear, similarly to these low-s or GAM functions. So if we use both solutions, logarithmizing the response variable salary and using polynomials degree of the predictor age, and still have the interaction of health, and plot our model, we will get even nonlinear relationships with the All effect function. Again, that's why I love it. It can plot anything. That's why it was the first function I presented to you. Again, we can plot this on the same plot, which makes the plot even more appealing. And we can also check the plot model results with these coefficients. Here. So you see, we have our effects of the first polynomial degree of h and the second polynomial degree of h, which allows us to do these parabolic relationships. Sometimes checking against the null hypothesis is not enough for some scientific papers or for some presentation, and we can improve it by adding just one argument to our function plot model, share values. So, and if we do this, we will get exactly the same plot, but we will get the estimates. That's what we always wanted. Not always, but that's what we wanted to visualize. And we will get the significance levels on the same plot. And this looks much more appealing than the table, because all people do are looking at the estimates to see the slope and looking whether the slope or effect is significant. And that's what this plot is offering to you. We can make it even more appealing. As I told you, we can use some new themes and make it look nicer, or even I like this one, even more nicer. Good. So now, why did we do this? Because we checked assumptions and they were not really satisfied. Let's recheck our assumptions and we will see that our correlation become lower. That's nice. Our residuals became more normal. We can see it here. The curve looks really like a bell curve. And all these strange numbers went to the very, very end of the residuals plot. And at the very, very end, it's kind of okay to have some deviations. The main important thing is that these high leverage people who earned a lot of money, they are gone. You can still have them here, but the residuals became more normal. That's how you can do and plot nonlinear models. All right? But again, we just talked about GAMs, generalized additive models. And of course, there is a possibility to do it yourself, not only with the ggplot2 package. And in this package, you have to be careful, or with this function, GAM function, you have to be careful because there are several packages. One is GAM and another is MGCV package, which have the same function. And they have something in conflict. So please don't use this function if you want this function to work. If you want function from the GAM package to work. Sometimes it's useful to pre-write the package, double point, and then write the function from this package. So this GAM is package, and this GAM is function inside of this package. All right. What we do is exactly what ggplot2 just did. It uses this smoothing factor and just smoothed stuff. And how generalized additive model works is pretty interesting. It cuts the x-axis in several pieces and plots the simple linear model to every piece of this, and then connects these linear models to one nonlinear. Okay, we have our salary. Let's call it this salary. We have our data D. And we have our variable year. We already know how it influences salary. If you just leave and don't do anything, the salary will grow because of the laws of economics. We also have age. We also have seen that the older we grow, the better our salary will be. We have studied education, and we have studied job class and its influence on the salary. So now let's use the nonlinear model, generalized additive model, and put all of these arguments into the model. For the numeric arguments, we have to use the smoothing factors. For the categorical, not. So if we plot this, we can see all these results in the same plot immediately. And the crazy stuff is that this nonlinear model caught the crisis of 2007 and 2008. You see that the salaries go down, and it was the crisis, while the linear model did not see that. Again, with the age, we saw that the older we go, the more we will earn. Is it true? No. The nonlinear model showed the reality, particularly that you earn a lot and your salary might grow until you are 40 or 45. Then you hit this optima, and then your career kind of stagnates until you are going to the pension. And if you're retired, your money will probably go down, but we are uncertain about it. So you see how different the story is if we look at the nonlinear modeling. And with these functions, plot GAM, you can tell the really nice story. Interestingly, the education and job class or any other categorical predictors did not really change. The results were really similar in the linear models. I love them. So now we are, of course, at the logistic regression. We have to visualize logistic regression because it's one of the most used classification algorithms if we talk about it in a fancy machine learning terms. But it's actually one of my favorite models because logistic regression is amazing. It shows me how the world works in terms of probabilities. We always plot the probabilities from 0 to 1, and despite having just 0 and 1 response variable, we will get all the possible percentages, 30, 50, 60% in between 0 and 1, and I love it. Again, we already know what health is. We have we have two levels of health. This would be our 0, like bad health. Let's call it the bad health. And this would be our 1. Let's call it the good health. And the model will measure the probability to be in a good health depending on the job class, which we already know, and health insurance. And the health insurance also has two levels, yes and no. And in order to use the generalized linear model or logistic regression, we have to specify the family binomial. And binomial is because we have only two possibilities in the response variable. It is binomial variable, yes and no. So we can produce our model. And again, using only this argument, which we already know, we will immediately get a result. Isn't it amazing? And don't forget our plot model, which is really nice. You remember we could use this model or this function plot model to get the estimates. We could use this function to get the estimates with the significance levels and numbers. Or we can use it, as you already have seen, to get the interaction effects. Again, we could use the immense function, which we already used for the post-hoc, to figure out what is the difference in job classes depending on the health insurance. And if I look at this, we will not have any difference. If I have insurance, it doesn't matter where I work, I will be in good health. And if I do not have a health insurance, the probability to be in a good health is really low, independent of my profession. Yeah, that makes sense. If we do it differently, like we did previously, we just exchange the order of the predictors, we will see that industrial workers and information technology workers both have significantly different outcome of their health depending on the insurance. So if we have health insurance, we will be significantly more healthy independently of the occupation here and here. Again, we also can do the interaction term and display all of our results pairwisely. In this case, with 4 groups, we have 6 different pairs. So we have to take 6 tests and adjust p-values of these tests for false discovery rate. We might have used another method to visualize these p-values. And there is a bonus number 4 where we can visualize the post-hoc analysis and the pairwise p-value plots. Again, using the immense language, we produce the pairwise comparisons. We adjust our p-values exactly the same like here. And we use the PWPP, which means pairwise p-plot function, to display all these p-values. So on the x-axis, we will have false discovery rate adjusted p-values, and we will immediately see which are significant and between which groups exactly. It's even color-coded. And of course, to make the plot looks more nice, we can add some arguments which will quickly change the appearance of this plot. So you see, in this way, you can report a lot of interesting results without having these not pleasant to the human eye tables. But again, why do we do this video? It's because a picture is worth 1,000 words or 1,000 numbers. Now, let's get to the slightly more complicated logistic regression. In the usual logistic regression, we have 2 levels of the response variables, 0 and 1. That's why we write family binomial. In the other variables, which we still want to check the probability from, we might have 3 or more levels. And that's where the multinomial logistic regression helps us to visualize it or to check the probability of 3 or more levels in the logistic regression. So we will do it via the neural networks. And in order to do this, let's get a new data. You have to install the foreign language before. And from this language, we'll only use one function once. That's why we don't need to load it like red library. We don't need to do this. We just say, take from the foreign language, please, this function and read the data. If we do this, we will have read the data. You need the internet connection for this. And if we have a glimpse of the data, we will see interesting stuff. And the response variable proc has 3 levels. So can we do this with logistic regression? Well, yes. We have the neural network package. And from this package, again, we only need a multinom once. That's why we don't load the whole package in order to avoid conflicts between packages. But we can use the neural networks package and multinom function once. It will understand what we want to do. We only have to provide arguments data. It will understand that the data is, and the formula similarly to what we already done. And amazingly, even these complicated models can be plotted with our favorite function, plot all effects from the effects package. Isn't it cool? We even can plot it together like this. Look at this, isn't it cool? I pretty enjoy working with this package. Beautiful. Now let's get to the class of models, which is very, very complex, mixed effect models. I will not explain what it means, but I will show the difference between the usual linear models and the mixed effect models. For this, of course, we need some packages. We load these packages. We produce some data. This data is already inside these packages. SIT9 will produce exactly the same result as in this presentation. And let's just produce two models. First of all, we produce a linear model, and we have a multiple linear model with mixed effects. And these are the mixed effects. These are repeated measures. If you don't understand what it means, it's okay, you don't have to. The point of this video is that you can visualize these models. And of course, we have to compare them before using the one or the other model. And we see that model 1 has a slightly lower AKX information criteria, which is the indicator of the model quality. Lower means better, and it is significantly better. So we have to go with this model. You can compare these models and see that the model with repeated measures or with mixed effects is much better, significantly better than the model without mixed effects. So we have to go with this. Again, we use the same function, our favorite all effects function, and if we plot this, we will get beautiful plot. I just want you for a second appreciate what we do here. We use a very complex model. It is a multiple model. It is still linear, but it has mixed effects in it. It has interactions in it, and it still can be plotted like this. These kind of models also can be checked with the immense package for the contrasts, so we can check the difference, significant difference or not between these groups. And we again, as we have learned in another bonus, can plot the adjusted p-values, or even not adjusted p-values, we can specify this, on the beautiful plot which is worth the whole table. So if we just use this line with the multiplication, you will never put this into the paper. This you can. That's the advantage of the visualization. All right? So let's get to the more complex things. Now we learn how to do nonlinear models. We learn how to do and visualize the mixed effect models. And of course, there are some nonlinear mixed effects models. It's already the next level. It's really rarely used. I don't think you will need it, except you work in the medicine field. I sometimes use it because I work in the medical field as a researcher. And if we use this package, MG as this, which visualizes the GAM, multiple generalized additive models, and it also has random effects in it, we can plot this just like that. And we have the usual generalized additive model, nonlinear, but we accounted for the random effects, which will make our model much better and our fit much stronger. All right, so let's get to a completely new way of analyzing data. It's a survival analysis. You might have heard about this. For this, we have two response variables: a time, which will be a numeric variable, and a status, which will be a categorical variable similar to the logistic regression, 0 and 1. If it is 1, the animal died or the person died, and if it is 0, it did not die, it was censored. So you see, we did the simple linear regression, we did the simple logistic regression, and now we kind of connect them and use the numeric variable and 0 and 1 categorical variable together to make a survival curve. If you didn't heard of this, it is a Kaplan-Meier survival model. Again, you have to install the packages, you have to load the packages, we will get some data and manipulate it, and then using the surf fit function, we can create our model, right? And we can visualize the model using the GG surf plot function. Why do we always have GG? Do you know this? It comes from the ggplot2, which means grammar of graphics. So it's really, really state of the art. And if we execute this, we will get several curves which come from this variable. We have 3 levels of these variables. we can go one step further in comparing the curves between each other and see whether there is a difference in the median survival time between these categories. For this, we will just allow the p-value to be true, and this function will make a real test and compare them. If we do this, we will get the significant results, which will say that these curves have significant difference in the median survival time. And it does not tell you between which and which, so we have to do a post-hoc analysis and produce the pairwisely p-values to see between which curve the median survival time is different. And for this, we can do pairwise surdiff function and see that between level 0 and level 2 of the pH-cog variable, there is a significant difference. And also between 2 and 1. All right? Good. The problem with the Kaplan-Meier survival model is that it can only handle one variable with several levels, but still only one variable. If you want to have several variables, we have to go to the Cox models. And if you want some smoother parametric variable, we have to go to the exponential parametric models, because this is not smooth, this is not parametric. You cannot predict from this. That's why we can go to the exponential parametric model and do the same, really the same modeling, but parametrically, smoothly. And if we execute the exponential parametric model and just plot it, we will get the same results, but smoothly. And with this, we could predict the future. We can check exactly what survival time will be here, and it will be much more exact than with the Kaplan-Meier curve, because between the events, if nobody dies, the probability of survival don't change, which is not really real. The probability of survivals, if it declines always. And this model is therefore more realistic. So, and the last model we want to visualize is the Cox Proportional Hazard models, and we have the same variables, time and status, and want to check the hazard ratio, how dangerous it is for the people depending on their age, sex, and pH-cog. And as I said before, here by the Cox model, we can use several predictors which we cannot use with the Kaplan-Meier curve. And ggforest function can just take our model and visualize it pretty quickly. This is really nice plot, and it's kind of a similar plot to the plot model function from the sjplot package. It shows us the coefficients or estimates of the model for every predictor. It shows the estimates here, the p-values or significance level here, and it also shows the confidence intervals and even the number of observations every predictor had in order to produce this plot. It also shows you the archaic information criteria, which is the quality indicator of the model, and if we have two different models, we can compare them and see which is better. And it also shows you the global p-value, and the global p-value is small, which means the model shows something significant. Alright, I really hope it was useful for you. If you found some value in this video and want to see more, please consider liking and subscribing to my channel, and leave a comment if you have an idea about the future video. So, stay healthy and see you in the next video. Cheers!